Now we want to look at even more limited circumstances where we can use the range equation. And so before, we looked at the special case of projectile motion, where we had a coordinate system parallel and perpendicular to the Earth, and we had a projectile with some launch speed v at some angle alpha naught, where we assumed the launch point was at the origin of the coordinate system, and we looked for a relationship between its vertical and horizontal position at some arbitrary later time. And so now we want to add an additional circumstance where the final y position is equal to the initial y position. So we're looking for the condition where in the y-axis it comes down at the same level where it started. And now we are seriously limiting our range of applicability, but you can see why this is useful. You can use the range equation as long as it's not too far, flat Earth approximation and all that. Of course, we're neglecting air resistance, but if you're launching something from the ground and it comes back to the ground, then something like the range equation would be applicable. Okay, so we're going to go straight to the projectile motion equation that we had before, which told us that the final position y is equal to tangent of our initial angle alpha naught times x minus acceleration due to gravity to initial speed squared cosine squared of our initial launch angle times the final position squared. And so if our final y position equal to our initial y position, given our assumptions, this is equal to 0. So if this now is equal to 0, the first thing we can do is factor out a divide by one factor of x, and then that gives us, it would then sort of bring tangent on the other side. Well, we'll bring the other on the other side, bring this term on the other side to make it positive, and so we'll have g over 2 initial launch speed squared cosine squared of launch angle x is equal to tangent of the launch angle. And so now what we want to solve for is x, which is where the range equation comes from, right? We're going to solve for how far in x does the object go. So then x is equal to 2 initial speed squared cosine squared of the launch angle over g times tangent of alpha. If I separate that out, that's sine of alpha naught over cosine alpha naught. We get one of our terms of cosine alpha naught to cancel. And I'm going to rewrite this a little bit. Is initial speed squared over g times 2 cosine alpha naught sine alpha naught. And this, if we remember our trig identities, is equal to sine of 2 alpha naught. So there we have it, our range, which is sometimes just called r, which is the distance in the x dimension given that the final y position is equal to the initial y position, is v naught squared over g times sine of 2 alpha naught. And from this is where you get the expression that this is maximized for alpha naught equals 45 degrees and other things. So remember, this is still only true for no air resistance. So it really doesn't have great applicability in real life. If you're going to look at projectiles, you really have to take into account their resistance, and also the very limited circumstances of projectile motion that we discussed before, with the initial constraint that the final y position is also at 0, equal to the initial y position. But if we have all of those circumstances together, we really do have a handy expression that will save us a lot of computational time.